Okay. So chapter 8, we're beginning with section 8.2 because 8.1 is the use of a bunch of tables, so it won't be really necessary to test on that. Going right into 8.2, number 39, and the topic is integration by parts. So when you have a mix of what's called an algebraic term and a trigonometric term, then you have to come up with another situation or another solution than u sub, because they have nothing to do with each other for u sub. And we don't have any other formulas that allow us to figure this out. So the easiest way to identify what to use for u sub, even though it's not a technical u sub, is the acronym LEAD. The higher up you are, that's what you're going to assign your u, and the rest, or the other one's going to be your dv, if you remember doing that. We're going to break this up into u dv. So we're looking at this as the integral of u dv, two pieces that have nothing to do with each other, and their answer becomes uv minus the integral of v du. And hopefully the result will allow us to integrate this combination, even though we weren't able to integrate this combination. So I don't have anything that's logarithmic, I don't have anything that's inverse trig, but I do have an algebraic term. So I'm going to let u be x cubed. That means the du is 3x squared dx. dv is the other portion, which is cosine of 2x dx. And its integral, right, because I'm differentiating this way, but I'm integrating this way. So the integral of cosine is sine. Imagine having to balance this with a 2 and a 1/2. Alright, so the parts that we're going to use for this, we're going to use our u and our v first. Minus the integral of v du. Okay, and you're going to notice pretty quickly, I'm going to clean this up a little bit. By bringing the 1/2 and the 3 out. You're going to notice pretty quickly that although this is a smaller exponent than we had before, it's only slightly better than what we started with, even though we've included all of this work. So imagine doing this again and getting us down to an x, and then doing it again and getting it down to no algebraic term. So we can continue in this direction, but I'm going to try and save time with what's called the tabular method. Also, one thing to keep in mind, if you continue in this direction, once you do your uv on this, it has a 3/2 out front, a negative 3/2, so you're going to have to distribute that in, and it can get really messy really quickly. The alternative is the tabular method, which looks like this. I don't know why I label it u's and dv's, or I suppose I should just do u and dv. But your u, again, is x cubed. Your dv is going to be cosine of 2x dx, although we can leave the dx. And because it was a positive integrand, I'm going to put a plus here. This table is only as large as we need it to be to continue to take derivatives of x cubed until it becomes a constant, or until it becomes 0. So the derivative of x cubed is 3x squared, followed by 6x, followed by 6, and then followed by 0. Okay. The integral of this, we saw the first one, and it was 1/2 sine 2x. And I hope that draws your attention to the fact that the coefficient will be the reciprocal of what's inside. So the integral of sine is negative cosine, but because it has a 2 here, it's going to become negative 1/4 cosine. The integral of negative cosine is negative sine, but because I had to balance it, it becomes negative 1/8 sine. Do it one more time. The integral of negative sine is cosine, and by balancing with the 2 and the 1/2, I get 1/16 cosine. These alternate until you get to the bottom. And to finish the structure of the tabular method, our arrows of connection are going to go directly left, and then they're going to drop. So this +0 is representing our plus c that we're going to have at the end. Now pause for a second. You can see that there's 1, 2, 3, 4 separate terms. That means that we would have had to go through this 4 times up here. It can get really messy. Now all I have to do is combine these different arrowed motions. So I've got a positive x cubed multiplied by 1/2 sine x. In other words, I'm going to write x cubed over 2 sine 2x. Followed by a negative 3x squared with a negative 1/4, or better yet, a positive 3x squared over 4. Then I've got 6x and negative 1/8. I am going to simplify that to negative 3x over 4. Negative 6, positive 6, 1/16, that becomes negative 3/8. And then this +0 is the plus c that we need at the end. Okay. Let's look at that. If there's any questions again, just unmute. Otherwise, we will continue. I would recommend the tabular method for any integration by parts where you have a mix of algebraic and anything else. And the algebraic is an easily differentiated power rule. Just remember that as you take the derivative of this, I'm covering it, but as you're taking the derivative of this, you're going to have more than that exponent of these different combinations. So that's why I would recommend going to the tabular method instead. Even for number 40, even though it's x squared, I still think it would be beneficial to go ahead and use the tabular method for it. So we've got the integral of x squared e to the 2x dx. Again, look at the acronym LEAD. I don't have a logarithmic, I don't have an inverse trig, I do have an algebraic and an exponential. Up here I had an algebraic and a trigonometric. So the algebraic, the one that's listed first, is your u, and your dv is the other portion. I start with a positive x squared, and I'm going to put e to the 2x over here. First thing I like to do is see how long this table is going to be by taking the derivative of my u until I get 0. That means this is going to be a 4-lined table, 4 rows. I'm also going to imagine taking the integral of e to the 2x, and in so doing, I'm imagining putting a 2 next to the dx and balancing it with a 1/2 on the outside. So I get 1/2 e to the 2x, and then I'm going to get 1/4 e to the 2x because the integral of e to the u is e to the u. And then finally I get 1/8 e to the 2x. For a final answer, of x squared times 1/2 e to the 2x minus 2x over 4 e to the 2x plus 2 over 8 e to the 2x minus 0 or plus c. All right. 1. We're now in trig integrals. I have the integral of, and I'm going to write this. I'm going to write this next to each other. So it's sine to the 5, or sine to the 5th power, sine t to the 5th power, and then this is going to be cosine to the negative 1/2 t. The reason I'm going to bring it up is because I already know it's not a u sub. If it was a u sub, I would allow the denominator, the cosine, to be u, and I would have a negative sign by itself as the du. But then I've got 4 extra signs to worry about that I don't want. So I know that this is going to fall into the trig integral category. I can't do anything with fractions or negatives, so I know that this is not going to be the one that I'm going to play around with. If this is immovable, then cosine has to be my u. That means I'm going to have to play around with my signs to figure out what the du is and convert the rest of them. Okay? So if cosine is my u, then du is going to be negative sine t dt. Alright, we'll keep that in mind for later. That means that I have to save a sign for my dt. But it's not just a regular sign, it should be a negative sign. Balance it. This portion right here is all ready to go for a cosine integral, but this sine to the 4th is getting in the way. I'm going to do some manipulations down here. Sine to the 4th power is equivalent to sine squared squared. I know that sine squared is equivalent to 1 minus cosine squared. So what I'm in essence going to have to do is double distribute 1 minus cosine squared t. I'm going to look before we end here to see if the identities are given to you, but if there's any that aren't given to you, this would be one of them. This is one that everybody should know. The fact that sine squared plus cosine squared of whatever variable is equal to 1. So you should definitely know that before going into the final exam. And that's all I did here. I replaced sine squared with 1 minus cosine squared. And I get 1 minus 2 cosine squared plus cosine to the 4th, which is going to go in place of the sine to the 4th that I have at the top. I also like to remember that I put this box around so that I don't confuse going into it or multiplying into it. It is done, it is saved, it's in a box, it's saved for later use. The rest is what I can multiply and manipulate. This cosine to the negative 1/2 can distribute into this trinomial, even though it's in parentheses, it's raised to the 1st power, so it is penetrable. I get cosine to the negative 1/2 t minus 2 cosine, well, 2 minus 1/2, right? Because technically I'm adding, so it'd be 2 plus a negative 1/2, but 2 minus 1/2 is 3/2. And then 4 minus 1/2, well, 4 is 8/2, so 8 minus 1 is 7/2. All right. I can write a u sub statement, but I already did up here. I said u is equal to cosine of t. So keeping that in mind, this is u to the negative 1/2. This is negative 2u to the 3/2, and this is u to the 7/2. So I can just integrate them separately at this point because I have the du appropriate for all of them. Cosine to the negative 1/2 becomes cosine to the positive 1/2 over positive 1/2. So when I say over 1/2, what would have been my denominator becomes my numerator's coefficient. Cosine to the 3/2 becomes cosine to the 5/2 over 5/2. And cosine to the 7/2 becomes cosine to the 9/2 over 9/2. To clean this up and finish it off, I'm just going to rewrite it as negative 2 cosine to the 1/2 t plus 4/5 cosine to the 5/2 t minus 2/9 cosine to the 9/2 t plus c. And I will say, in a final exam situation, I feel like this is much more larger than I would do. I wouldn't raise something to a 4th power, but I wouldn't be opposed to raising it to the 2nd power. So we'd be skipping this middle step and having something a little bit more easy to manipulate. Okay. Again, if you have any questions, just unmute. Otherwise, I'm going to continue. 43, I've got tan cubed 2t, secant cubed 2t dt. When I have secants and tans, I have a couple options. If secant is my u, then I would have to save one secant and one tan for its derivative. As long as my leftover tan is squared and I can convert that using an identity, then that's okay. So this is possible to turn everything to secant. The alternative would be if I had tan bu, then I would need to save a secant squared for its du. If I saved secant squared, that would leave me with one secant, and I can't convert one secant to a tan. So the decision's been made. I'm going to have to let u be secant, whose derivative would be secant 2t tan 2t times 2 dt using the chain rule. Alright, so I want you to imagine one of these tans being reserved and one of these secants being reserved, leaving tan squared, secant squared, and then, I ran out of room here, but secant 2t tan 2t dt. The only thing that's missing for its derivative is a 2. So if I put a 2 with it, then I have to balance this with a 1/2. I know that's squeezed in there, so I'm going to go to a fresh sheet after this. All right, let me rewrite that. This is 43. I just said that I had a 1/2 on the outside. I've got tan squared. I've got secant squared. And then I've saved now a 2 secant 2t tan 2t dt. And that's all part of the derivative. But secant tan is the derivative of secant. These are fine, these are not. So what can I do to get rid of tan and make it appear to be a secant? Well, if I remember this identity, then turning it into a secant identity would mean that I have to I'd have to incorporate a division of cosine, right? Because the reciprocal of cosine, 1 over, is the secant that I need. So I'm looking at the new identity, tan squared plus 1 equals secant squared. can either have that memorized or just know that it's easily manipulated from the original identity. All right, so tan squared is going to get replaced with secant squared minus 1. This secant squared is fine, and then the 2 secant 2t tan 2t dt is still reserved for the derivative. Just like in the last example, this is a set of parentheses raised to the first power, so secant can be distributed in, giving me secant to the fourth 2t minus secant squared 2t would be appropriate 2 secant 2t tan 2t dt derivative. Now that everything is converted to a secant, everything being what's not in the box, I can just treat it like a u sub. If u is secant, then du is the secant tan. Or better yet, if u is secant to the secant of 2t, then secant 2t tan 2t with the 2 in front is what I need to integrate this. Secant to the fourth, or u to the fourth, becomes u to the fifth over 5. Secant squared becomes secant cubed over 3. And then to clean this up, I get secant to the fifth 2t over 10 minus secant cubed 2t over 6 plus c. That was a distributing rather, of the 1/2. Okay. So that was trig integrals. We're going to jump to trig sub now. Let me keep track of these on my notes. We started with 8.2. Did we skip a 42? Let me see here. Okay, that was 42. Oh, I never did 41. Okay. After this, we'll go back and do 41. Actually, I'll do 41 right now. I'll just write a big old oops. Sorry about that, everybody. So we've got the integral of the natural log of 2x over x squared. Otherwise, you can look at it as the natural log of 2x, x to the negative 2. The reason I bring that up is because if I have the natural log over x, then I know that that's just a straight up u sub. But this is a different version of x. It's not just a single x. So, according to Leate, the natural log is going to be my u, and the algebraic term is going to be my dv. If u is equal to the natural log of 2x, then du is 1 over 2x times 2 dx, or, better yet, 1 over x dx. dv is x to the negative 2 dx, and its integral is going to be x to the negative 1 over negative 1, or, better yet, 1 over x, negative 1 over x. So when I put these together, I get uv minus the integral of v du. Clean this up a little bit. I've got the natural log of 2x, or the negative natural log of 2x over x. plus the integral of x to the negative 2. Final answer is negative natural log of 2x over x times x to the negative, or I'm sorry, plus x to the negative 1 over negative 1 plus c. I could clean this up and write, instead of x to the negative 1 over negative 1, write it as negative 1 over x, but I ran out of room. I would encourage you to rewrite it, though, as negative 1 over x. Okay? I apologize for skipping that one. That was a silly mistake. Alrighty. So back to trig sub. On question 44, and it says the integral of 1 over x square root of 4x squared minus 16 dx. Okay, I know that this is going to be trig sub because I'm seeing a square in the beginning and the end of my binomial inside the radical. That's something that I have been trained to look for in terms of secant. Secant is sticking out to me. However, be mindful, if this is u squared minus a squared, then the u is 2x, right? Because if that's u squared, it's got to be the square root of that to make u. And that makes a 4. Now, secant also needed not partially u, but a full u on the outside. If I put a 2 here, then I balance it with a regular 2 outside. I also need to keep in mind that if I have a u of dx, or if I have a u of 2x, then du, which is 2dx, needs to be balanced in the integral as well. I have dx, throw a 2 in with it, balance it with a 1/2, and the 2's ended up canceling. So the integral I'm technically looking at right now is the integral of 1 over u radical u squared minus a squared du. Okay? Now I already told you that that is your arc secant formula. And I'm going to solve it that way, but I want to go back. I didn't technically use trig sub to do this. I need to go back and show you how to do trig sub. So again, this is an inverse trig, which leads us to 1 over a arc secant of the absolute value of u over a plus c, which is 1/4 arc secant of the absolute value of 2x over 4 plus c. Now, what's nice about that is that we can check to see if we're doing it correctly, if we have the right answer from this trig sub. So trig sub says, okay, you think that looks like the secant? Let's say that it does. If that's the case, then u, which we're saying is 2x, is going to be equivalent to a secant theta. Du, which is 2dx, is equal to 4 secant theta tan theta d theta. Right? The derivative of u is du. The derivative of 2x is 2dx. The derivative of 4 secant theta is 4 secant theta tan theta d theta. If I substitute in for everything that I see, then I have an integral of 1 over, I still need a 2x, right? I still need a 2x. So everything would still balance if I put in the 2, balance it with a 2. Or let's say for a second that you didn't balance. Let's go up here. This x didn't originally have a 2 in front, so let's just pretend for a second that it's an x by itself. If that's the case, then if I solved this for x, I would divide both sides by 2, right? So x alone would be 2 secant theta. Four x squared is like saying u squared. So it would be 4 secant theta squared. I'm showing you this the long way. There are shortcuts to it, but for right now I'm just showing you exactly what the long way would look like. And this 2dx was just a dx by itself. If I did dx by itself, I would have to divide both sides by 2, leaving 2 secant theta tan theta d theta. Everything that's in there now is either trig or a constant. These 2 secants can cancel. This becomes 16 secant squared theta minus 16 times tan theta d theta. 16s can be pulled out. And hopefully you remember that secant squared theta minus 1 is equal to tan squared theta. I also hope that you remember that if we have a product of radicals, I can separate them into 2 individual radicals. So my integrand now becomes 1 over 4 tan theta times tan theta d theta. In other words, I'm integrating 1/4. That's it. The integral of 1/4 would be 1/4 times the variable. In this case, it would be theta. All right. Now, I can't keep it in terms of theta. I wouldn't get full credit for this question. So I have to go back and figure out what theta would be based on my u statement. Everything always comes back to the u statement. If I want to solve for theta, let's see, this becomes x over 2 equals secant theta. If I want to solve for theta, I'd have to arc secant both sides. So this is telling me that my answer is going to be 1/4 times theta, which is arc secant of x over 2 plus c. Does this coincide with what we figured it out to be before? Absolutely. Now the absolute value of 2 is obviously a positive 2, so the 2 and the 4 here could cancel to a 1/2, and this one's 1/2. The reason this one doesn't have absolute value marks around it is because in order to do trig sub, it's assumed that you're in a certain quadrant. It's assumed that you're using a certain domain. That wouldn't be necessarily the case up here, so we had to restrict it. Okay? I feel like this question is a little bit more difficult because we have more than one choice. We could easily go in a direction that we're not supposed to. 45 is less like that. 45 is more where we absolutely would need trig sub. And I'll go through the thought process as to why trig sub would be used. So it's not u sub, because if u was x squared minus 6x plus 5, then du would have to be 2x minus 6, and I don't have the minus 6. I could do a plus 3 minus 3 and balance it all weird up there, but I'm not going to. There's other things I could probably try, but I'm not interested in that. Right now what I'm interested in looking at is the fact that this x is written first, which is usually the case with a secant. However, this doesn't say u squared minus a squared, okay? And I would want it to be a difference of squares. And the only way to do that would be if I had, if I did completing the square. First thing you have to realize is that the coefficient here is 1, so we're good to go there. Take your b term divided by 2 and square it. And I get 9, which means that I need a 9 here, and I will balance it with a minus 9 afterwards. It turns my first 3 terms into x minus 3 squared, and it turns that into a minus 4. Now I have u squared minus a squared. Even if 4 wasn't a nice square number, let's say it was something like 5, then you would just treat a as the square root of 5. So everything here, as long as it is an integer, a negative integer, we can take the square root of that a portion. Alright, so anyway, u is going to be x minus 3, and du is going to be dx. Okay? But because this is trig sub, I have to remember that when my u is written first, it's a secant prompt. So this is going to become a secant theta, whose derivative is a secant theta tan theta, d theta. And I'm just going to substitute in exactly what I see. I'm not going to try to balance this. I'll balance it later. I'm just going to substitute exactly what I see. So if I have an x by itself, imagine this statement being solved for x, I would get 2 secant theta plus 3. So x is 2 secant theta plus 3. My denominator, and I think for review, I'm just going to keep doing these the long way. X minus 3 is 2 secant theta, so this is going to become 2 secant theta squared minus 4. The dx is 2 secant theta tan theta d theta. After all the substitution is taken care of, I take a moment to clean up what I see. 2 secant theta plus 3 in the numerator. Denominator becomes 4 secant squared theta minus 4. I will skip one step. We've already seen in the last example 16 secant squared minus 16. So I do want to kind of guide you through the thought process of factoring out a 4 and then having secant squared minus 1. So this becomes the square root of 4 times secant squared minus 1, which is tan squared. Remember, this breaks up into 2 separate radicals, so I get 2 tan theta. That's nice because it gets rid of my tan theta. It also gets rid of my 2, leaving me with the integral of 2 secant theta plus 3 times secant theta. Or better yet, 2 secant squared theta plus 3 secant theta d theta. Now, I can't do a u sub because I don't have a secant theta tan theta that's appropriate for a u being secant. But secant squared theta should stick out to you, and we should just know how to integrate secant theta. I'm positive that the integral of secant theta will be provided to you for the test. The integral of secant squared, well, that's the derivative of tan theta. And I'm going to run through why this answer is what it is, but you can reference this on the sheet that you're going to be given. But secant theta is really 1 over cosine. And I remember taking notes back in the day where we included like a 1 plus sine, something like that. And we ended up getting sine on the top, cosine on the bottom, and pretty sure This ends up being a positive natural log of secant theta plus tan theta plus c. I'm sure you don't want to bank on a pretty sure, but I'm like 99% positive there. Okay, this is not the final answer. So we go back to our u statement. Now, if we just had a regular theta, we could plug in, but we've got different functions of theta. And when I see sines, cosines, tangents, secants, cotangents, and there's more than one of them there, I know that I'm going to have to use my triangle to figure out all the different pieces. The pieces that I do know are all based on the u statement. Okay? Secant of this theta, secant is the reciprocal of adjacent over hypotenuse, so it's hypotenuse over adjacent, is equal to this statement solved for secant. So if I solved this for secant, I would get x minus 3 over 2. And then adjacent would be the bottom, and the hypotenuse would be the top. The Pythagorean theorem would give you the other side. If I solve this for b squared, that's what you would get. That should look familiar. We had that before. So x minus 3 squared minus 4. I'm going to leave it like that. You can simplify that into x squared minus 6x plus 5, but it's not necessary. You can leave it like that as well. So tan is going to be opposite over adjacent. Maybe I will simplify it since that's where we started our original. Plus 3 natural log of secant. So let's see, secant would be x minus 3 over 2. And then tangent would be square root of x squared minus 6x plus 5 over 2. So I am going to clean this up. Maybe I won't just because I don't really have room. But my 2's would cancel, and I would probably write my natural log statement as one fraction. I would put x minus 3 in parentheses. I would add this square root and put them all over 2, probably. But that would be your final answer for this. I feel like 45 is kind of challenging, especially since it takes up a full page. So this would be a good problem to practice during like a homework session, but you can rest assured that on a final exam it wouldn't be this difficult. Just by judging 46 looks more like something you would see on a final. At first glance, I see a number before the x squared. So as I'm looking at this, I'm thinking u sub doesn't work because I don't have just a regular x that I can manipulate to a negative 2x. And then if I'm thinking a squared and u squared, I'm thinking sine because the a squared is written first. So let me assign these numbers. If a squared is 25, then a is 5. And if that's the case, u would just be x. So if I continue with trig sub, keeping in mind that the number's written first, then my u would be 5 sine theta. And the derivative of u is du, the derivative of x is dx, and the derivative of 5 sine theta is 5 cosine theta d theta. Subbing out what I have, I'm going to take x and make it x squared, which makes this 25 sine squared theta. I'm going to take the square root and I'm going to leave it as 25 minus x squared, which is 25 sine squared theta. and my dx is going to get replaced with 5 cosine theta d theta. Hopefully you can kind of foreshadow that the 25s are going to get factored out, leaving 1 minus sine squared, which becomes cosine squared. And then we've already discussed what happens here. This becomes 5 cosine theta, which will cancel with that 5 cosine theta. The 25 can come out front. It's not helping our integral at all. But at this point, I'm kind of stuck. You know, I can resort back to trig integrals to see if there's a strategy to use. And strategies for sine cosine are basically looking for which one is odd. And we don't have one that's odd. I can't reserve a sine and convert everything to cosine. I can't convert to cosine period because then I'd still be in a squared situation. So I should reference the different, oh my gosh, the word's escaping me, identities that I do have at my disposal. Again, the most obvious is sine squared theta plus cosine squared theta equals 1. There's the secant tan one, and then there's a cosecant cotan one, but those are not going to be helpful here. There are identities for, like, sine 2 theta would be 2 sine theta cosine theta, but that's not helpful here. That's sine 2 theta, not sine squared. And then there's 3 identities associated with cosine squared theta. And off the top of my head, I don't know what they are. If they're not given to you and you need them for the test, I will make sure that I include them. But I'm just opening up to the back of the perforated sheet. And sorry, I wrote that wrong. We've got cosine 2 theta, and that's equal to cosine squared theta minus sine squared theta. It's equal to 2 cosine theta minus 1, and it's equal to 1 minus 2 sine squared theta. And then if you look further, so we're not in a situation where we have a double angle, so neither of these is going to be helpful. But if you look further on this perforated sheet, again, I will include these with you, there is another way to write sine squared, which is 1 minus cosine 2 theta over 2. Okay. Now you can see that if it introduces a double angle, then this step prior will be necessary. But I can substitute out a sine squared for a regular cosine, which is something I am going to want to do. Sine squared is going to become 1 minus cosine 2 theta over 2 d theta. That 2 can come out with the 25. And maybe I think of it as 2 separate integrals at this point. The integral of 1 and the integral of cosine 2 theta d theta. The integral of 1 will just be theta. And I can't take the integral of cosine of u unless the u is balanced. So introduce a 2 here with a 1/2, and I'm going to get sine 2 theta. Let's see. Theta is going to be equivalent, if we look back here, to the original u statement. If I solve that for theta, I get x over 5, the arc sine of that. The 25 and the 1/2 are going to distribute, and I get 25 over 4. 25 halves and 1/2. 25 over 4. Sine 2 theta, right? I can't just do that, so I'm going to bring it back up to this, sine 2 theta, and I get 2 sine theta cosine theta plus c. Clean it up a little bit more. I know I'm kind of taking my time a little bit on this one. Now there's a major problem with my answer. I've got x's and I've got thetas. You can't have both. So these are the ones that are going to convert based on the triangle. And the triangle is based on your u statement right from the beginning. If u is x and x is equal to 5 sine theta, then x over 5 is the representation of sine of this angle. So x over 5 are your opposite and hypotenuse. If you do the Pythagorean theorem, you're going to get 25 minus x squared for your third side. So now to finish up this statement, I get 25 over 2 arc sine x over 5 minus, we get 25 over 2, sine will be x over 5, cosine will be square root of 25 minus x squared over 5. So the two 5's in the denominator are going to cancel with that 25. Right? Sine ends up being over 5, cosine ends up being over 5. These become a 25, which cancels with that 25, leaving sine, which was x, and that one's going to be 25 minus x squared over 2 plus c. I apologize for skipping a step, but I ran out of room. Let's check in with this page. Thank you, Max. Unmute yourself if I see the 41. I went back and saw that, but I didn't see any conversation. I can only hear you guys because I don't have that screen up. So if something like that happens again, just let me know. All right, 47. Now we're doing partial fractions. We've got 1 over 4x squared minus 9dx. Partial fractions means that these denominators can be factored down into linear and irreducible quadratics. This is factorable. It's equivalent to 2x plus 3 and 2x minus 3. Because both of those are linear, then I can say that that fraction is equivalent to some constant, because it's going to be, we're going to be using u sub, and since this is linear, I have to go down a degree, so down a degree from a linear would be constant, and this is equal to some constant that might or may not be, that may or may not be the same as the other constant, so we're going to reference them differently. If I want to solve this, going back to algebra 2, then I need a common denominator over here. Which would be the 2x plus 3 times the 2x minus 3. The a fraction is missing the 2x minus 3. And the b fraction is missing the 2x plus 3. Once the denominators all match, you can ignore them. So what I'll often do is immediately jump to this step. I'll say this numerator is equal to a times the other denominator and plus b times the original denominator, or the first denominator. You have a couple options to solve for x and to solve for a and b. Not solve for x, but rather a and b. One option is you can let x be specific numbers that will turn this into 0, and then that requires us to solve for the b. Like if we let this be 0, then the a is going to go away, and if we let this be 0, then the b is going to go away. Another option is if you can't figure out that this is supposed to be positive and negative 3 halves, you can pick any number. I'm going to pick any number for this one, and then I'm going to be more intentional in the last one, or the next one. So let's say I can pick any number. If I let x equal 0, there's no rhyme or reason behind that other than the fact that it's an easy to manipulate number. If I let x equal 0, then this statement now reads 1 equals a times, that goes away, leaving negative 3, plus b, that goes away, right? 2 times 0 is 0. Positive 3. In other words, negative 3a plus 3b. Now that's not going to help me get an answer until and unless I pick another x value that introduces another, I guess binomial or whatever, and then we're going to have to do elimination to figure out these two. So I want to do that just in case you don't pick the right numbers right away. But just know that if you pick the right numbers right away, we would have had an answer for A or B already. All right, if I let x equal 1, then I get A equaling 2 times 1, which is 2, minus 3, which is negative 1. And 2 times 1 is 2, plus 3 is 5. So then I would put these together. And I need to eliminate, so I need something that's going to eliminate nicely. If this right here was a positive 3, then they would eliminate nicely, which means I would have to multiply my entire second equation by a negative 3. Negative 2 equals negative 12b, so b is equal to 1/6. And then if I plug 1/6 back into one of those equations, this becomes 5/6. If I subtract that from both sides, I get negative 1/6 equaling negative a. In other words, 1/6 equaling a. Let me make sure I did that correctly. Negative 2 divided by negative 12 is 1/6. 1/6 is 5/6, turns this into 6/6. 5/6 from 1, or 5/6 from 6/6 becomes 1/6. Oh, sorry, that'll be a positive, and then that'll be a negative. Okay. So I'm going to change this a up here to a negative 1/6, and I'm going to change my b to a positive 1/6. I like to start with my positive number first, so when we get back into our integrand, I'm going to rewrite it as 1/6 over 2x minus 3 minus 1/6 over 2x plus 3. That's just my preference. And usually I start with my subtraction first, and if that was the case, then I wouldn't have to worry about changing the order. But all right, treat these as two separate integrals. I think it would be much easier if I actually wrote it that way. So I've got 1/6 times 1 over 2x minus 3 dx minus 1/6 times 1 over 2x plus 3 dx. If I do u sub, then u is 2x minus 3 and du is 2 dx. So I need a 2, balance it with a 1/2. Same here, I need a 2, balance it with a 1/2. So now I've got 1/12 of the natural log of 2x minus 3 minus 1/12 natural log of the absolute value of 2x plus 3. And since they're both 1/12, this is my preference. You don't have to do it this way, but I am going to write this as a single quantity. I'm going to leave 1/12 as a coefficient, even though you could treat it like an exponent. And I'm going to treat this subtraction problem as 2x minus 3 over 2x plus 3. You do not have to do that. You could have left it alone, but I like to see it that way, personally. All right, 48. The integral of x squared minus x plus 9 all over x squared plus 9 quantity squared. This is an irreducible quadratic, so when I break it up, it's going to look like x squared minus x plus 9 over x squared plus 9 squared. When you break these up, you write them down as their original exponent, so x squared plus 9 to the first power, and then you represent every increasing exponent until you get to the one that you see. Luckily we see a 2, but if this was a 5, then you would see x squared plus 9, x squared plus 9 squared, x squared plus 9 cubed, and so on until you get to x squared plus 9 to the 5th. So these are the two denominators that I'm looking for this. Heaven forbid there was a linear here as well. I would want to represent that, but for whatever you have, if it's squared, then you write it as the first power and the second power. Because it's a quadratic, 1 degree less than a quadratic is a linear, ax plus b. 1 degree less than a quadratic is a linear, cx plus b. I have to use different letters because they might not be the same. So x squared minus x plus 9 is equivalent to ax plus b times what it's missing. Well, if it has 1 x squared plus 9, it's missing the second. And cx plus d isn't missing anything because it already has the largest exponent of the x squared plus 9. This goes into that. I'm going to distribute and rewrite this a little bit more cleanly. I've got ax cubed plus 9ax plus bx squared plus 9b plus cx plus d. That means I've got ax cubed plus bx squared plus the quantity 9a plus c, all tagged with an x, plus 9b plus d, the constant term. So this is another strategy to solving this question. If I write it out this way, then I'm assuming that the coefficients line up. Since there's no cube over here and there's x or ax cubed over here, I can assume that a must be 0. Since the coefficient of x squared is 1, I can assume that b is 1. I can assume that 9a plus c is equal to the coefficient of x. Lucky for me, I already know what a is. So c is -1. Let's see. If b is 1, then this is 9 plus d equaling 9. Well, that can only happen if b is 0. So going back to my integral, it is now going to be the integral of ax plus b, in other words, 0x plus 1 over x squared plus 9. And I'm going to automatically separate it into two separate integrals. Minus 1x plus 0 over x squared plus 9 squared. These integrals look awfully similar, but they are solved very differently. The first one is an inverse tan function. The second one is a u sub because the numerator is 1 degree less than the denominator. This one becomes 1/3 arc tan of x over 3. And this one, if it's u sub and x squared plus 9 is my u, then I have to balance it with a 2x and a 1/2. Now this reads 1 over u squared, or u to the negative 2, which becomes u to the negative 1 over negative 1. Clean it up, I've got 1/3 arctan of x over 3 plus 1 over 2 times x squared plus 9 plus 8. Okay, I would probably say that it's safe to assume 8.3 and 8.4 are the two hardest lessons of the chapter. So if you want to concentrate and practice those, I would definitely recommend doing that. All right, we are jumping to 8.7, L'Hopital's rule. L'Hopital's rule is a nice refresher after some of the intensity that we've just been working with. We need to learn how to do L'Hopital's rule because it comes back in 8.8 with improper integrals. So if I plug in -1, my numerator gives me 2 plus 2, which is 4. I'm sorry, 2 plus 1, which is 3, minus 1, so or minus 3, which is 0. I end up getting 0 over 0. That's what I consider the type. This is a 0 over 0 type. I can't simplify that. It's not a good type, and if you remember from our limit chapter, we needed an alternative method, and a new alternative method is L'Hopital's rule. I'll usually script it with an LR as a reminder that I'm applying it, and L'Hopital's rule says take your limit expression and differentiate the numerator and the denominator in their own line. The limit of this function will equal the limit of the derivatives function. So the derivative of 2x squared is 4x. The derivative of -x is -1, and 3 disappears. The derivative of x plus 1 is 1. So the limit of this function is equal to the limit of this function. They're not equal themselves, but their limits are equal. The derivative gives us 4x minus 1. When I plug in -1, I get -4 minus 1, which is -5. Done. Once I'm able to evaluate it, then I should do so. We've got the limit as x approaches 3 of the square root of x plus 1 over x minus 3. If I plug in 3, I get the square root of 4 in the top, and I get 0 in the bottom. That would just be one of the infinities, but I'm going to change this. So if you're with me, by all means, I apologize, I should have had this done already. I want this to be 0, so that would have to be a 6. No, that would have to be -3, right? This is what happens when I try and do stuff in the moment. That would be 0, okay. So I'm going to do this, and then I'm going to do a side note and provide a different question. But if I plug in 3 right now, I get the square root of 4 over 0, 2 over 0. This is going to be, like if you have 2 pizzas and the slices are really, really tiny that they're almost 0, you're going to have infinitely many of them. The positive infinity because of the positive I had in the numerator. Although actually, if this was approaching 3 from the left, we would get a negative down here. It would be positive negative infinity. So I am going to leave it alone for right now, but show you what I really wanted to do. do in capital letters. Instead, try the limit as x approaches 3, the square root of x minus 3 over x minus 3. This is another 0 over 0 type. Again, it's poor planning on my part. So I'm going to do L'Hopital's rule, giving me 1/2 of x minus 3 to the negative 1/2 times 1 over 1. I am going to take a moment to clean this up. Notice I didn't write LR here because these are equal to each other, not just the derivatives based on L'Hopital's rule. Alright, now I'm going to have 0 in my denominator. Okay, and I might not like that. I might want to do this one more time if you want to. 1 over 0, but we can integrate that. 1 over 0 is going to be infinity. If I did L'Hopital's rule one more time, I would push that to the top, and I would end up with infinity anyway. So let me show that just as proof. I would have evaluated it here, but if I did L'Hopital's rule one more time, what I would have gotten is, nope, I would have gone back into this system. It would have been 0 over, or 0 regardless. Okay, bad question, sorry. 50 did not do what I wanted it to do. 51. Alright, if I plug in infinity, I'm going to get infinity over infinity, so that is the type. Apply L'Hopital's rule. The derivative of the natural log is 1 over x, and the derivative of x squared is 2x. Simplify this, and I get 1 over 2x squared. If I plug in infinity, I get 1 over a giant number, so my limit is 0. Much more like the question I would prefer. 8.8. Alright, so we've got question number 52. The integral from 1 to infinity of 5 over x cubed dx. You cannot write 1 to infinity. That would be like, you're still getting your point across, but it would be like in English not having a capital letter in the beginning of your sentence or a period at the end of your sentence. So there is a grammatical element to this. Instead, you write it as the limit. In this case, I'm going to write as b approaches infinity from 1 to b of 5x to the negative 3. I want to write it in that form so that I can integrate it pretty easily. The reason I'm writing b is because we treat the upper bound as a b and the lower bound as an a traditionally. But you're going to want to look for whatever number is making this difficult. Like in the next example, infinity is still difficult, but maybe 0 if I plugged it in would be difficult, or something like that. If in the next example it said 1 minus e to the 0, or 1 minus e to the x, then 0 would be a concern because it would end up giving me 0 in the denominator. But for right now, this is the one that's the concern. If I integrate, I don't do limit yet, so if I integrate this, I end up getting 5x to the negative 2 over negative 2. Take a minute to clean it up. And just like we did with any definite integral, we're going to plug in the upper bound and subtract the lower bound. I always like to take a second to clean up what I just did. This is now going to become plus 5 over 2. All right, and now we theoretically approach the limit that still has the b in it. If this denominator is approaching infinity, then this entire fraction is approaching 0. 0 plus 5 halves is a final answer of 5 halves. If you want to double check that you did that correctly, you can always write this integral in your calculator from 1 to 100, and then 1 to 1,000, and then 1 to 1 million, and see if you are in fact getting numbers that are closer to 2.5. Alright, infinity is the problem, so I'm going to do the limit as b approaches infinity from 0 to b of e to the x, 1 plus e to the x in the denominator. At the same time, I'm treating this like a u sub, but in an effort not to introduce more variables than I can handle, I'm just going to imagine my u sub. My denominator would be u, 1 plus e to the x. Du would be e to the x dx. So this really says 1 over u du. And I know the integral of 1 over u is the natural log of u plus c. In this case, I don't do plus c because it's a definite integral. I'm going to plug in b, and then I'm going to plug in 0. If this is growing toward infinity, then the natural log of it is also growing toward infinity. If this is 1, then it's minus the natural log of 2. The natural log of 2 is almost completely irrelevant when compared to infinity. So the final answer is infinity. All right, and that is your Chapter 8 review. Chapter 9 will be done tomorrow.